welcome to another seminar of our institute. Today's speaker is Pavel Kroupa, whom I think you almost all know. So I will only briefly say that his path started in Insitute in the Czech Republic, where he was born. But then his path became incredibly complicated, and it covers nearly the whole globe. And it went through Southern Africa, Germany, Australia, where he studied master studies, then to Cambridge in England, where he did his PhD, to Germany again, where he obtained his associate professorship, his habilitation or docentur in 1992, and then in 2002, and then in 2004 he went to Bonn, where he became a professor. And since 2016 he became a member of our institute as well. His topics of scientific research are quite rich. So I will only say that somehow unifying topic is stellar population and stellar populations and stellar dynamics, which covers nearly the whole universe. So he is trying to find out how the universe works, how it looks like out there. So I'm very happy to have him here today again after 2 years. And he will talk about how the formation of star clusters works, and that it maybe works a little bit differently than we thought. So, please, the stage is yours.
So thank you for the nice introduction, and it's a pleasure to be here again and give this presentation on a project which we did somewhat surprisingly last year. It was not planned, but a publication appeared, and we reacted to that publication. That's the consequence of this talk. So it's concerned with the Orion Nebula Cluster, and this is what we are talking about. So we have here Orion on the sky, the belt of Orion, and in the sword of Orion are 3 stars, and the central one is actually a whole star cluster. It's 1 million years old. It looks like this. So this is the central star in the sword of Orion. It's surrounded by this nebula. It's actually part of a whole molecular cloud. And here are ionizing stars, O stars, which are just in this moment halting star formation, destroying this cloud from within. On this one object, there have been about 1752 publications in this time, and so it's a bit surprising that one can still find something rather new in this object. It is the closest star-forming region which is forming massive stars. It's about half a kiloparsec away from us, and the only one at that distance which is actually making massive stars. So that's why it's particularly interesting. Forming massive stars is a very rare event. All the star formation happening between us and half a kiloparsec distance are forming lower mass stars. So this is a more detailed image. We have here at the center that what is called the trapezium. It has a dimension of 0.05 parsecs. Going from here to there it takes only about 10,000 years for the velocities of the stars in this object. So it's a very dynamic structure, and as you can see, it's extremely young. It could be much younger, but date aging stars is difficult at this age. Contains about 1,000 stars, and here's now the detail of the actual central part of the trapezium. This is θ1 Orionis, which is doing the ionization. It's about 50 solar masses. That is what is basically destroying the cloud. You can see the effects of the radiation and the stellar wind from the star on the other low mass stars, which are flying through the central region and interacting with the radiation and the gas in this area. Now this part is basically void of gas already. The gas has been blown out, there are detailed studies of the gas flows in here. It's a very complicated structure, but gas is basically leaving with a fairly high velocity from this region. If we go a bit to the left, so this is the trapezium here, we can see these objects which are now in the more, somewhat more distant region. still within a parsec or less than a parsec, but further away. And you can see these, what are called proplyds, and this black dots. If we zoom in on this, we realize that these are actually forming stars at the moment with accretion disks. So this is a face-on star with an accretion disk, and this is a more an edge-on star with accretion disk, and a remnant of its protoplanet, proto-stellar envelope is still visible, being ionized by theta 1c, which is here. So it's basically like a cometary structure. So in these circumstellar disks, which are about 1 million years old, probably now planets are forming. That's why this is also a very interesting object, because we can actually see the initial conditions, at least probably the initial conditions for planetary system formation. What we do seem to understand today is that we have this cloud, and the trapezium is at this point, it's blown a bubble into the cloud, which is active. It's very dynamic, so this is ongoing. Within probably tens of thousands of years, the morphology will be extremely different. It wouldn't be recognizable as we see today. Gas is flowing out here because these stars, the massive star here, especially the one in Orion C, is ionizing the gas. So this front, ionizing front, is moving inwards while the gas is blowing out. And then we have all these thousands of low mass stars which also formed it. Behind this is another clump which is forming stars actively. And all of this is very compact. You can see this size is about 0.7 parsecs. Looking at the stellar population in this object, so we have again 1 parsec, and this is at the center is the trapezium we just had. Hillenbrand did a remarkable study of this object, taking spectra of all of these young stars, thousands of spectra. This was an incredible effort. She's now a professor in, I believe, in Caltech, from such data, one can construct HR. So first of all, one gets the densities. There's a very dense structure. You can see nearly 100,000 stars per cubic parsec in this inner region, while near the sun we have a density of 1 star per cubic parsec. Okay? So you can see that this is a really extremely dense region. One finds then the HR diagram or color magnet diagram. So this is the effective temperature, this is the luminosity of the stars, and all these stars from this Hillenbrand survey are well above the main sequence. This is the hydrogen burning main sequence, and all of these stars are well above the main sequence, so they are indeed very young. It's not clear whether they're 500,000 years old or 2 million years old, but there's a dispersion. The dispersion can be because of gas effects of gas obscuration, but also variability. These points move around because the stars are excreting and changing luminosity. But we are clearly looking at something which is extremely young. So this is the 0.1 million years isochron as an example. Now, that is not the only cluster. If you want to understand how star clusters form and where stars come from, we have to look also at other objects. So there's, for example, the Pleiades cluster, which is about 100 million years old, might have started with a few thousand stars and is at about a distance of 120 parsecs. Then we have this object here, which is NGC 3603, which contains about 10,000 stars and is again about 1 million years old. And you can see it's very compact. And then we have this object here, which is contains 100,000 stars. Again, it's very compact. This is about 5 parsecs, and this is in the Large Magellanic Cloud. So this is 50,000 parsecs away from us. So we have these 3 or 4 extremely well-studied clusters. The Orion Nebula Cluster, the Pleiades, NGC 3603 and R136. And we can study these to try to understand what the initial conditions were in a mathematical sense at t equal to 0, which doesn't exist in nature. But in order to mathematically and physically model this, we need to have some sort of starting time. And so we want to understand how we would mathematically describe this object at t equal to 0, basically. And so this leads us now to the initial cluster radii and the expansion problem. We see that these very young clusters are typically very compact. What we also observe is the open star clusters, like the Pleiades, are much more expanded. They are typically a few parsecs large. That is an issue. How do we get these very young clusters, which are so compact, to these larger sizes, which older clusters, older than something like 50 million years, have. And this size difference therefore constrains the formation of these clusters. There are two possibilities. The one is that these clusters form hierarchically from smaller subclusters. This is favored by many in the community, perhaps related to lambda CDM cosmology, where this concept of hierarchical merging is rampant. But another possibility is that these clusters actually form in one monolithic collapse in a dense molecular cloud core. The question is what is happening. It has implications. So we can test the hypothesis that the merging happens. So the cluster doesn't form as we see it, very compact, but it forms from a number of smaller clusters, which then with time merge. And that is already the problem. This merging needs time. And we've studied this. So this is here the time. This is the spatial dimension of these subclusters. And depending on the mass of this, we can constrain the initial size given observed clusters. The result is that this doesn't work. So for the very young clusters which we see, like the Orion Nebula Cluster, NGC 3603 and R136, there's not enough time to actually build up the cluster from smaller structures, unless these smaller structures are so compact that it's basically anyway a monolithic collapse. Yeah? So that's an important result. Remarkably, if you study the literature in the which is being published on this topic, they neglect the timescale argument. They just do these type of simulations and say that they can get something which about looks like the cluster, but it might take too long, is typically not discussed, which is quite a remarkable situation. So we can therefore now conclude that the typical present-day density of and the size and very young age and near-spherical core halomorphology of gas-free, very young, massive clusters like R136, NGC 3603, and the Orion Nebula Cluster dictate an episodic or monolithic, near-monolithic formation of such star clusters, undergoing violent gas dispersal. And this is now the next problem. So we see that they must form very compact and quickly. The question is, how do they then become big? Yeah? First of all, we wanted to ascertain that not only these very young observed clusters are formed so compact, but the typical open cluster also forms so compact. And there is a way to do this, because if you have a cluster which is 100 million years old, you can, of course, you have enough time to form it through many mergers. Yeah? So how do we constrain this? And there is a nice trick or approach. It's not a trick, but it's a nice approach. And that is by using the binary star population in these clusters. With binary stars tell us how compact the cluster must have been, assuming that the binary star energy distribution function is universal, for which there is good evidence. So if we assume that the stars form according to a universal birth distribution function, like this one here, then, for example, Taurus, which is only about 100 parsecs away from us and forming only small, low-density clusters with low-mass stars, then we find that the shape of this, basically the longest period orbits which are in the cluster, constrain the density of the cluster to not be higher than a certain value. Because if it were more dense, these binaries would not be able to survive. They would be broken up. And the same we can do, for example, for the Orion Nebula Cluster. So we have here a cutoff in the period distribution function, and we can model it with this initial distribution function, which is not plotted here, but this distribution function is depleted. These binaries are disrupted. They are long period binaries because the binaries in the cluster, they move past each other and then they are ionized, they are dissolved. And this cutoff then constrains the shape of this observed distribution function of binaries, tells us how compact the cluster must have been. Now, what is being plotted here, sorry I didn't mention this, is the fraction of orbits versus semi-major axis. So to read this, it tells us that this data point implies that there are about 12% of all the objects in this cluster, 12% of the stars have a companion within a distance of some 200 or so astronomical units. Okay, and here we see that about 4% of all the objects have a stellar components at a distance of something like maybe 500 astronomical units. Okay, that's how one would treat this diagram. So given this analysis, we looked at all these objects, which are, for example, Ophiuchi, Taurus, Praesepe, Orion Nebula Cluster, Pleiades, and we calculated the initial density these clusters must have had to match the present day observed binary distribution, so the energy distribution function of the binaries. And so this is the density in solar masses per cubic parsec, while this is the mass of the object when it formed. And you can see, and these are globular clusters, for which we have independent estimates of their birth densities. You can see globular clusters formed very, very dense, and they are, of course, at a much more massive scale. Now, the open star clusters and the lower mass clusters you can see here are much less massive, and they form at a lower mass density. And the interesting result is that these inferred densities, birth densities, are in very nice agreement with observed densities in molecular cloud cores. Okay, so this is a nice consistency check that the calculations from the binary stars actually agree with what we see in molecular clouds, and that's, these are these points here. And so we do have good evidence that all these open and also globular clusters formed very compact with extremely high densities even here. And this then implies this radius-mass relation. So this line is this radius-mass relation. So a star cluster, which we see on the sky, like the Pleiades, would have formed with a radius which is given by this relation, and that's the birth mass of the Pleiades, which could have been something like 2,000 solar masses. So you can see that it formed very compact. Now that's an analysis of star clusters. And so a consistent, using different arguments, picture emerges. Stars form in very compact embedded clusters. So now we can look at the evidence from actual molecular clouds. What is the evidence there? Because remember, if one wants to build up an understanding how these objects form, we want to use various different evidence to see if all of that evidence points in the same direction. Because if you follow one argument and it tells you something, and another argument tells you something else, and they don't agree, then of course we will not gain an understanding unless we understand why they wouldn't agree. So that's the idea here. And there's some very beautiful work done by Philippe André in Saclay near Paris. This is from a nice review where they looked at Herschel data of a particular cloud. So it's this region here in Taurus. And they found that the dense gas and the dust is in these filaments. Now these filaments are remarkable because they are incredibly small and coherent over incredibly long distances. So you can see that this particular filament extends many parsecs, and it's much less than a parsec in cross-section. Furthermore, if one looks at detail at the velocity structure and the density structure within such a filament, we can see that these filaments are made up of subfilaments, which themselves are coherent over parsecs and a few parsec scale in velocity space. So what you see is that the gas along this red filament here, for example, is actually coherently moving. It's a long structure which is moving in the clouds, and then there's another filament, like this green one here, which is even longer, superimposed on that. So there are these filaments which are moving together in this dense structure, these observations basically destroy the theory of graboturbulent formation of stars, because these clouds are obviously not turbulent. It is not possible to have in a turbulent gas medium such long coherent in phase space structures, and that's where the stars form. We know that the stars form along these filaments. In the denser regions, we form a higher density of stars, and that's where little clusters form. So we see also that there are these perpendicular structures. That's where gas falls in. So gas is flowing in from the interstellar medium, which is now molecular, into these filaments, which then build up. And for presently not fully understood regions, the clouds like to make these coherent filaments, which are incredibly thin and very long. And so these authors have studied the cross-section. So if you go back here, if you cut through here, one can measure the density across this, in this cross-section, and that's shown here. So that's the density of molecular hydrogen against the radius. And one can see that these filaments are incredibly compact, 0.1 parsecs. That's a typical dimension of these filaments, although they are some parsecs long. This model is what we refer to as a plumber-like model. So that is quite an interesting result. One sees that in this dense structure, the gas temperature is particularly small, which means that it's in this region, the gas basically stops moving. Yeah? It's extremely cold, coherent, and there are basically no motions anymore, except motions along the filament which move towards the density regions where the stars are forming. And so this is a histogram of the radii of the filaments, and we can see that they are indeed very compact, very comparable, and this is the beauty of this, with this result obtained from star clusters. It's basically the same number you see here. Yeah? And that's really nice, because we now know that these clusters, these very young clusters, they form in intersections of filaments, and they have a dimension which is well below 1 parsec, which is consistent with the derivation from the binary star and globular cluster analysis. So this is the picture. We have here a filament, and if this is an overdensity along the filament, then matter falls towards the potential minimum. That's what gravity, matter has to move like that. And so if a overdensity builds up along the matter, filament falls in, molecular gas falls in, as well as being fed from smaller filaments along the side, and that's where then these clusters build up. And there's some very beautiful work by Alvaro Hacar on studying the details of this, where he now became very famous because he was the first one to really look at the details of this these types of objects, writing some really most remarkable papers on this topic. So we have this result that these clusters form indeed very, very compact. And so we then have the problem. So this is, remember, this is the birth density versus mass. They form very compact. The question is, how do they become big? So this here is now the birth density divided by the present day density. So all these objects are today much lower density than when they formed. They are expanded, while these molecular clouds are still contracting, which is why they are below 1 in this case. So the molecular cloud cores are still contracting. These objects are expanded. So one has to move from here to there to explain these clusters, as well as the globular clusters. If we do an n-body model, so we take a star cluster and we do a high accurate, high precision n-body simulation, for calculating the forces between the stars very accurately, including binary star interactions, and stellar evolution, which means the cluster would like to expand because of mass loss from stars, the star clusters evolve along a horizontal line here. So if they start at that density, then they just move across a line. They don't change, actually. And that's the problem. How do we get them up here if they start at that density? Yeah? And so that problem is framed in the following. So we have these statements. Open star clusters are larger than what we observe for these very young objects. And this size difference constrains the formation of star clusters and the cluster expansion problem. They have to expand. So this is a more recent and more detailed n-body experiment, starting with star clusters here. That's the effective radius. A star cluster starting here or there. This is the time. And such star clusters with massive stars, they evolve. They are full of binaries, so there's a lot of binary activity. The clusters evolve and then they expand because of stellar evolution and binary star heating, but they do not expand sufficiently to explain the observed star clusters which are up here as shown here. So there are Milky Way clusters, local group clusters, so from the whole local group of galaxies, and forgot what this is, some other clusters. But anyway, these are all open, I think these are open galactic clusters. And the colors tell us the mass. So these yellowish ones are very massive, million solar masses, while these ones here are about in the range of 10,000 solar masses. So how do we get clusters which form at this size to those radii? This can work, and this is shown here, if the clusters expel much mass. So one artificially, one reduces the potential of the cluster, and then of course it will expand. And one does that through a low star formation efficiency. So if the clusters form very compact, and 2/3, so more than 50%, something like 60 or even 70% of the gas is removed and does not make stars, and is removed sufficiently quickly from the cluster, then the stars will expand, and that's what these calculations here show. So these are again n-body models, and a cluster which forms at this radius here, 0.2 something parsecs, will expand. At this point the gas is blown out. We would say this is the embedded phase. This is where the massive stars, the O stars, the ultra compact H2 regions break out, which means then the gas is ionized on a cluster scale, and then it erupts because it goes into overpressure and then flies away. So then the gas is expelled and the cluster expands. This is the effective radius, and you can see this sort of can explain these clusters, but more massive clusters can come to that regime, while the more massive clusters, you can see this color range, starting off somewhat larger, still sub-parsec, they then expand and can map out these observed clusters. So mass radius relation plus gas expulsion, and a lot of gas expulsion, is able to expand the cluster sufficiently to explain the observations. Can this work? Are the clusters able to actually expel the gas? So if we have a star cluster which only forms low mass stars, would it be able to actually generate enough energy to blow out a substantial amount of its binding mass? Remember that more than something like 60% of the binding mass has to be blown out. Okay, that needs quite a lot of energy. So is that sufficient? Does that actually work? And so that's basically a question of feedback energy. So the star formation efficiency issue, we do know that stars form from various observation surveys, stars form with a low star formation efficiency. So at whatever scale you look at, a whole molecular cloud means in a whole molecular cloud which is forming stars, only a few % of the mass goes into stars. If you go down into the star forming regions, something like 40% at most end up in stars. If you go on the single star scale, not more than 50% end up in the star from the surrounding molecular cloud's density core, which is making the accretion disk around the star. Star formation is incredibly inefficient, and it is self-regulated. That's what this means. Because if the stars blow out so much gas which would otherwise have gone into the stars, it's not gravity which does this star formation, but it's actually the stars themselves which regulate how much mass they take or how much they remove. So these numbers tell us, or this number tells us, that star formation is self-regulated. Gravity only starts the process. And that already destroys basically the whole theoretical framework of star formation we have today, which basically rests on the idea that star formation happens in graviton-turbulent molecular clouds, where the turbulent medium makes overdensities which then collapse to make stars. It might be part of the story, but definitely only a small fraction of the story, because stars formation is inherently, basically, completely self-regulated. Nature likes order, it self-regulates itself. That's basically what this means. So we have here very low star formation efficiencies. There's a beautiful survey here by Tom McGeeth at Toledo University, United States. They looked at the Orion cloud, the Orion Nebula Cluster, the Trapezium, the central star in the sword of Orion is just here. And that whole cloud, which has something like 1 million solar masses, maybe 100,000 solar masses, is making low mass stars just here, and they're all in these little clusters. And then in the north, up here, is the rest, is another part of the Orion cloud, which itself is again making these stars in these little embedded clusters. Only this object here is making massive stars. Everything else is not making massive stars. This again implies or tells us that star formation is self-regulated, in the sense that it's not stochastic. If it were purely stochastic, we would have as many O stars here as there, but none are observed. And it's a significant result telling us that the distribution of stars is not a stochastic is not a stochastic property, but it's a regulated structure or distribution function. So these observations by Tom McGeeth, who's a student, who used to be a student of Charlie Lada, who's at Harvard, have shown us, or confirmed basically, that the star formation efficiency is extremely small. So what we see here is each point is a cluster. So what they did is they looked at these clouds. You see all these little clusters. So these clusters have a certain number of observed very, very young stars in them, and that's what is plotted here. So these are the individual clusters. This is the Orion Nebula Cluster here. And depending on which traces they do and how they calculate the amount of gas in these objects compared to the stars, in all cases you see that the star formation efficiency is 10%, 20%. So basically you always see you see the molecular cloud core, which is on a scale less than a parsec, and only 10% or so of that is in the stars. And that's very consistent over a large range of masses, and depending on which traces one uses, whether one uses X-rays and infrared excess or some other scheme. So star formation efficiency is less than 40%, which means most of the gas is blown out. That's already a good sign for the cluster expansion problem. The question now is, how quickly is the gas removed? If the gas is removed very slowly, it might take too long to observe these very young clusters which are already free of gas. Furthermore, the expansion would be not as much. Because if it's a adiabatic process and the gas leaves very slowly, the stellar cluster will just expand together with the gas as it's leaving. And this might not be enough. And so we have here, again, this result. And the question now is, so that the star formation efficiency, which is the mass in stars divided by the mass in stars plus the mass of gas in that object. And the question is, how quickly can this gas be removed? That's the gas expulsion timescale. That gas expulsion timescale can be compared to the crossing time. So you have a little cluster, and the stars take time to cross through the cluster. That's the crossing time, which is given by the potential. And if this is short, if the gas is removed on a time shorter or comparable to the crossing time, it's an explosive phenomenon. If it takes many crossing times, then it's an adiabatic process, okay? And the question is, what is happening? So this is here a nice little table where we have the number of stars in a cluster. This is the number of stars, that's the mass of the object. And this is telling us if they are O stars or not. O stars are particularly important because they can basically instantly heat the gas to 10,000 Kelvin, which will then just erupt, basically an explosive phenomenon. And so only when we have sufficiently massive clusters do we expect O stars, because the stellar populations are not stochastic. Therefore, you need a certain mass to build up actually an O star, and that's what we see here. And then we can calculate how quick the crossing time is in clusters which have these properties and this radius here. And you can see the crossing times are very short. If the clusters are that size, which is realistic, the crossing times for these massive clusters become ridiculously short. I mean, 20,000 years. 20,000 years means basically that there's no room for the stars to form anymore. Yeah? And this is consistent with these objects being full of extremely massive stars. Somehow it seems that there things coagulate rather than actually form individual stars. But it seems the question is here, in this regime, is gas expulsion shorter than the crossing time? If the gas is expelled on a thermal timescale, so with 10 kilometers per second, then the gas expulsion time would be about 50,000 years, which is comparable to the crossing time, which would be important for the cluster expansion problem, because then it would actually work. And so just as a reminder of the timescales, the star formation timescale, so the time to make a single star, so a star builds up its mass to 95% of its main sequence mass within about 100,000 stars. To make a whole cluster of stars takes about 1 million years. So that's the hierarchy of timescales. And here are now some data. We know that the star formation efficiency is very low, and we can, from such observations, we see that these objects here are very compact. So that's already what I've said. Even in the antennae galaxies, these are at some megaparsecs distance 2 galaxies which are just now interacting very strongly. The star formation rate is very high in these galaxies, and one can see thousands of very young clusters forming. And partially the clusters are actually in clusters. And these objects are observed to have very high masses, and you can see they are still very compact, but they are also somewhat older, up to maybe 10 million years. But these very young objects are typically very compact. So this tells us that these objects are very compact. We've heard that before. And then there's evidence from the velocities of the stars in the Orion Nebula Cluster and R136 in the Large Magellanic Clouds, which have about these ages and these masses. And we can, the observations tell us that these objects are supervirial, so the stars are moving too quickly to what they should be moving if they were bound in a potential of the cluster. This is evidence that the cluster is expanding, because if the cluster is actually expanding, the stars are moving more quickly than they would in a virialized structure. So both are supervirial, which is an indication that the clusters are actually expanding. Then we have an energy argument. If we can calculate the binding energy of the cluster, so this is the stars plus gas for a size. That's just this equation here in erg. And then we have the crossing time for a cluster with this mass and that same radius. And we can now compare how much energy is in the stellar population compared to the binding energy of this object. So we have a 10 to the 4 solar mass cluster has a binding energy which has this amount and this crossing time, if this is 1 parsec, and a 100,000 solar mass cluster has this binding energy and this crossing time, if it has that size. Now, a single massive star with 15 solar masses injects 3 times 10 to the 50 erg per 0.1 million years, and an even more massive star injects 10 times as much energy in 0.1 million years. And so these numbers tell us that a single massive star, single O star basically, is indeed providing enough energy to overcome the binding energy of this structure. It all depends, of course, on how much of the energy actually deposited in the gas. That's not so clear, but there is definitely, from the energy budget, on a time scale shorter than the crossing time, these stars are pumping so much energy into the gas that, yes, it can blow the thing apart. And so nebular disruption is indeed probably very rapid. And so we have here the observations of the antenna galaxies. This is what I was just mentioning. There's one core of the galaxy, this is another one. You see these spiral tidal patterns. You can see that all these structures are young clusters. Now you look at this object here. This is not a single cluster, but it's a star cluster of star clusters. Hundreds of star clusters, each more massive than the Orion Nebula Cluster, are sitting together on top of each other in a hugely massive molecular cloud, which used to be here. So each point is a star cluster, and this whole structure is a cluster of star clusters. This here is actually an even more remarkable object. It's composed of clusters of star clusters, and then they are clustered themselves. This is a whole little dwarf galaxy, basically, within this galaxy. Now, this happens because these two galaxies interacted very strongly, and the interstellar medium collided, causing huge pressures. When the pressure is high, molecules form immediately. And when molecules form, the densities are so high that basically immediately stars form as well. And so that's why this very active star formation happened. Now, observations of the gas motions around these objects tell us that the gas is moving away at this velocity, which means the gas evacuation timescale is indeed very short. Then we have this treasure chest cluster, which is a very young cluster. You can see it's supposed to be less than something like 0.2 million years. So it's just now in the process of forming. It's very compact. And the gas here, the ultra-compact H2 region, is expanding with a velocity of about 12 kilometers per second. So again, the evacuation timescale is very quick. And then we have, and so we can now say, in the presence of this evidence, that so in the presence of O stars, explosive gas expulsion may drive early cluster evolution independently of cluster mass. So, realistic N-body experiments, how does a cluster react actually to the expulsion of gas? So this is an N-body movie. Each point is a star. It's red because it's embedded in gas. At some point, the gas is blown out with 10 kilometers per second, and then the cluster expands because most of its gas potential is gone because the gas is blown out. You can see that it expands, but you can now see that a part of it recontracts. So although the dominant or a large fraction of the stars actually expand outwards, a part of the stars actually don't make it and they just fall back together. Yeah? So that's a revitalization, and now we formed a star cluster with a lot of stars around it which are now part of a tidal tail and part of the galaxy already. So this is, for example, Sambaran Banere doing these calculations with the ARSES code. This is Sverre Arseth, who's been developing these codes since 30 years. Most remarkable research, without whom we would never have been able to do these calculations. The work of Sverre Arseth is as significant as that of mathematicians who invented the ideas of, for example, integrations. Without Sverre Arseth's work, we would never be able to do the type of work we are doing now on a very many different types of research problems. And this is now just a particular detailed calculation with 10,000 stars, including brown dwarfs. Every star is in a binary. The cluster stars are very compact with a very high central density. The embedded phase star lasts 600,000 years, and the gas expulsion goes with 10 kilometers per second. And 1/3 of the gas is of the mass is in stars. And so we can see that the cluster expands. So this is the radius against time. This is 1 million years. That's when the gas is expelled. The cluster expands. And the nice result, I don't want to now mention explain the details too much, but the nice result here is that at this point the Orion Nebula Cluster is extremely well represented, and at this point we actually for free get the Pleiades cluster. Yeah, so it revitalizes and then it forms a long-lived open cluster which looks like the Pleiades. So the Pleiades, which is here, and this is the time, would have formed with a much higher mass. We have this sort of cartoon where we see the Orion Nebula Cluster evolves to the Pleiades within 100 million years, which includes a major expansion of the cluster to the Pleiades scale. This is just the center of the Pleiades. But if we calculate further, we actually get the Hyades cluster for free as well, which is remarkable because we have one sequence from Orion Nebula Cluster up to Hyades covering 600 million years. It's all basically one and the same type of cluster. So we have here the sky. You can see here the Pleiades. So the Orion is off horizon here, but we see here the Pleiades, and this here is the Hyades. And all these three objects are basically snapshots of the same type of cluster. I think this is amazing. So here, this is again the sky. You can see the Orion Nebula Cluster is here. This is where the Pleiades are, and that's where the Hyades are. So in the winter, when you look out and you see these three objects basically together on the sky, you can see an incredible phenomenon because you can see basically the same type of objects at different ages. Why we happen to have that sort of coincidence is remarkable, but that's just what it is, because all of these clusters are visible with the naked eye. They are at very different ages, but they all started off basically as the same, very similar objects. So it's really quite a nice coincidence. So here's another image where we have here see the belt of Orion. That's a sort of Orion, and here we have the Pleiades and the Hyades. So the destruction of the gas is evident in this cluster here. You can see how it's removed the gas. You can see the destruction. See the cluster is expanded. The destruction of the cloud is very nicely visible here, and we can also see here. This is a nice sequence put together by Wolfgang Brandner, where he shows that these clusters, which are observed at different ages, you can see 2 million years, 1 million years, going up to 10 to 12 million years, and one can see that they actually do get bigger physically. So the scale here is always the same. This is, you can see, this is 1 parsec, and this 1 parsec is true in all of these images. So yes, the clusters actually expand. We've done these calculations for all these different clusters. As I mentioned, the Orion Nebula Cluster, this cluster here, and this cluster in the Large Magellanic Cloud, using exactly the same numbers, just for different mass scales. So this is 1,000 solar masses, that's 10,000, and this is 100,000 solar masses. And these three numbers lead, with a radius mass relation, which we've inferred, lead to very nice reproductions of these clusters as they are observed. This is quite a remarkable result because basically we only need these three numbers to understand how star clusters form and then evolve. So the star formation efficiency is low, the gas expulsion happens with about 10 kilometers per second, and the delay time, so the compact time before the gas actually erupts, is about 600,000 years. So we have a very good understanding of the formation and evolution of very young clusters. This has been achieved. And this is what I was supposed to be talking about, but I can see that I've run out of time. I'm very sorry about it. I sort of timed it a little bit. It's not too long anymore. It's actually not, so I can maybe continue. Because this image which I've just shown, so the theory we now have where cluster forms monolithically, expels the gas and the show is over, actually it doesn't work. And that's the recent results which we found, and that's sort of the interesting topic. So we have, you remember the slide, and the question is how can would one expect something new? And that's the beauty of it in astronomy, that you look with new instruments and you will find something new typically. And that's this paper from the European Southern Observatory team, Giacomo Beccari, Monica Petter-Gotzens and Boffin and others. And they did this small, they used a small telescope by today's standards to do a new survey of this whole region. A very accurate, precise survey. They mapped thousands of stars and put them onto the HR diagram. So the idea today was that we have this cloud and the stars form and the stars disrupt the cloud, and then star formation is finished, and the new observations tell us that this actually doesn't work like that. So this is what they found. This is the magnitude versus color, and they found, so the main sequence is somewhere down here, and these stars are stars in the Orion Nebula Cluster, and they discovered these sequences. In fact, you can see here 1, 2, and there's a third one just here, which means the cluster is composed of 3 populations, which doesn't work if only one formation event happens, the gas is blown out, right? So how can that be? So here is the HR diagram, and these are the 3 populations. This is the youngest population, it's basically forming now. This is an intermediate age population, this is the oldest population in this cluster. And these populations have a different spread on the sky. So the Orion Nebula Cluster is just here. The oldest population is much more spread out than the intermediate population, and the youngest one is much more compact. Now, you see, when this paper was published, it's one of those events when you see a research result appearing which shatters what you knew until then. It's a remarkable experience. I've had it 2 times already in my life, where what you thought you understood, and then there's a completely new observational evidence, and you do not find a way to argue against it, rather than saying you don't believe the observation. That's a very poor argument. Many people argue like that. They say, I don't believe the observations. That's not how I would argue. I would always say, okay, unless this is wrong, and I know those people, so I do know that they wouldn't mess up scientifically, we have to take this serious. And the question is, how do we explain this, given everything we've learned until now? And that's the beauty of doing research, because you're suddenly faced with a problem which you haven't thought of before, but it's now there because that's what nature is telling us. And how do we solve this problem? That's what makes it exciting. And so for months I was thinking about this in the back of my head. I thought, well, when you don't see a solution immediately, the best is just to keep it in the back of your head, obviously. And then one day the enlightenment came, and it's really remarkable how these things come. This was actually here in Prague at a dinner in the conference, Model 17. I was sitting with Jerabkova and Dinbir, and suddenly it appeared to me that the way to actually do this is through the binary star activity, and it's a very elegant solution. So we have here the table where we have the older population. So these are still, this is about 1 million, 2 million years, 3 million years old, or 2.5 million years old. This is about a little bit younger, maybe 2 million years or so, a little older, and this is about 1 million years old. So we have these 3 populations, time scale of about 500,000 year to 1 million year between. So we have one cluster which managed to form one population, then it stopped, then it formed another population about 1 million years later, it stopped, and then it formed a third population again about 1 million years later. How does one do that? How can this be understood? And the model, and we can call it repeated stellar dynamical termination of feedback halted filament accretion model, the concept, the idea is completely trivial. Yeah? The idea is basically stellar dynamical ejection. So this is a bit too complicated. We've done before that, that's why I was able to think of this solution. We've done a huge survey with Sung-Kyung Oh about how young clusters expel stars if they have a lot of binaries in them. And So that's just Sung Kyung Oh and the huge survey she did with RZ's code. And this is a movie which you might now find interesting. It's a cluster which starts very compact. It has 3,000 stars in it. You can see how within a fraction of a very short time how active this cluster is. It shoots out stars all the time because of the binary activity. Binary has a lot of binding energy which can be transformed into kinetic energy, shooting out the stars. That's what we see here. See how some of them move very quickly. This is a 30,000 solar mass cluster. And you can see how within a fraction of a million years the stars are racing out. Even the very massive stars are racing out very rapidly. Even multiple systems are expelled, which are among the most massive stars in this type of cluster. You can see within a fraction of a million years, the whole field out to hundreds of parsecs is already filled with stars from this one cluster. And so that's basically the idea, that we have encounters which then expel the stars from the cluster. And we know from observation that 50% of all O stars are outside of clusters, 10 to 25% are moving rapidly, and this means that dynamical ejections are extremely important in the star formation process. And that's now the picture. So we form a filament, and here a star formation happens. A population builds up with massive stars. The massive stars ionize the gas and stop star formation. What then happens is that these massive stars, which are in binaries, eject each other. Okay, they fly out, the matter is still flowing in, it can recombine to make molecules, and then star formation again happens, building a second population, which again ejects its massive stars, and then the gas can recombine again. It's completely trivial, right? But it's an incredibly beautiful possibility, because we can now actually do some calculations. We see that with formation of a stellar population within less than a million years, then if the inflow of the gas here is in the range of 1,000 to 6,000 solar masses per year, we form about 300 to 2,000 solar masses in stars. In that case, only a few O stars will be there, and they will eject each other efficiently. These terminate star formation, but then eject each other. The gas recombines, and a cloud lives typically for a few million years, so this can happen and happen over and over again. And in the case when the inflow rate is less than 1,000 solar masses per year, no O stars form, and we form only one generation. If the inflow rate is larger than 6,000 solar masses per year, so the inflow along this filament here, one forms too many O stars, and again only one generation forms, because one cannot eject all the O stars. So we have a very nice prediction from this model, and we can now look at various clusters to see in the mass ranges suggested here, do we see evidence for this prediction? And so independent evidence are these stars, AE Auriga, Mu Col something, and Iota Orionis, which are far away, and they have been traced back with calculations in the galactic potential. We can see they are actually O stars here, and it's been found that they were ejected back, they went back to the Orion Nebula Cluster 2.5 million years ago, and I'm nearly finished. So, now, the interesting thing is that if we go back to the previous model I just described, and if we accept the result or the notion that the stellar population is not stochastic, but is a self-regulated distribution of stars, we can calculate the type of stars we expect in the various populations. And the remarkable result is, with that calculation, assuming star formation is completely self-regulated, we find a sequence of stellar masses which agree with these stars. Now, the oldest population formed about 2.5 million years ago, and that's exactly when these stars were ejected. And that's the type of stars we expect in that population if star formation is feedback regulated. And so this is the calculation where these three stars go back on the sky. That's where they originated, and they were ejected. And they are traced back to the Orion Nebula Cluster about 2.5 million years ago in this interesting paper here. And now, at that time, when this result was published, I ignored it, because I told myself, it's not possible that these stars, which are 2.5 million years old, could have come from a cluster which is only 1 million years old. But now it all makes beautiful sense, because the Orion Nebula Cluster actually kept making stars since 2.5 or 3 million years, and the truncation by the feedback, then the ejections of the massive stars will allow the star formation to continue solving this whole problem. And so a few points, just small telescopes can yield big results. Yeah, this is quite a nice consequence of this survey, especially if they are used by clever people like Giacomo Beccari. The detailed formation of star clusters has become a much more dynamic, interesting problem. It is actually incredibly beautiful how we can read off from the sky the detailed physical sequence of star formation over a few million years, even down to individual stellar masses. So thank you.
So thank you very much for your talk, and actually for perfect timing. And now we have some time for discussion. So please.
In global clusters, there are also, say, 3 populations of stars. So do you think that it is also due to this some oscillation process?
The multiple population problem in globular clusters is very different to this one here. Very different. Yeah. So in globular clusters, what we see is in the somewhat less massive globular clusters, where the stars have basically the same metallicity, so iron abundance, that they have anti-correlated elements. I forget exactly which elements they are, but sodium versus magnesium or something. Yeah? And they anti-correlate, which means they tell us that they are results of a nuclear fusion buildup. And so how that actually comes about is today not solved. We don't understand that. And this here is actually, as these stars are chemically the same, but they just formed at slightly different times. It's a different type of problem.
Are there any other cases than ONC?
Not so far, no. This makes it exciting, because if this is a correct description of what happens, we would expect in a certain mass range of clusters, and that's what was quantified in that paper we wrote, where we expect this phenomenon, where we expect multiple populations separated by about 1 million years, and beyond, so for more massive clusters and for less massive clusters we wouldn't expect this. So there's a prediction, and that's what now one can do. One can look at similar clusters. In our paper we mentioned another cluster which is in that mass range. One can now do a detailed survey to see if this actually is the case. Now, of course, it's not binding. Not every cluster will necessarily make multiple populations. It actually depends on whether the massive stars can be ejected. It's very likely, but it's not necessarily the case that every single massive star is ejected. And so it is possible that even in this mass range, we do find clusters which only have one population, but it's likely, very likely, to find multiple populations in that particular mass range, which I mentioned. Yeah. And so what we are now doing currently actually is with Humboldt fellow Long Wang, who came to us in Bonn, that he is now investigating how often do you actually expel massive stars from these clusters. That's an interesting problem, because it's basically, if you read our paper, you will see that it's in a sense speculative. I mean, I used estimates of how likely it is to expel all O stars from a cluster based on previous work which I was involved with. But the question is now, how likely is it? Is it 90% likely or just 30% likely? If it's only 30% likely to expel all O stars from a young cluster, then we are incredibly lucky to see the 3 populations in the Orion Nebula Cluster, which is the closest cluster which actually would be able to do this, right? And it becomes less believable. But if it's highly likely, then it's basically a rule, and then the question is, how do we get all the O stars being ejected? That's what we are working on now. We are trying to map out the parameter space. The parameter space is the core of massive stars, the size of the core, the number of massive stars, and the binary properties of the massive stars. And there is a certain range in this parameter space where basically every time all the O stars are ejected. The question is this solution a physically realistic solution given what we observe on the sky? And so that's a type of result, project or research which is now continuing from this. And of course there will be observational surveys to see if other clusters have this phenomenon too.
In your n-body simulation, how do you model that the gas suddenly disappears?
Yeah.
Do you model it? Because embodied problem, there is no gas.
That's an excellent question. So the problem is that a full-scale calculation with the gas is physically basically not possible. The reason, no, I mean, although a lot of people sort of try it, I think scientifically it's dubious to do that, because if you want to do a molecular cloud simulation, which actually makes stars, the problem is that you have to parameterize how the stars input the energy into the gas. This requires some heating efficiency, and then you have the outflows. How do you treat that computation in a gas simulation? With magnetic fields, you need magnetic fields to do the outflows. The outflows are actually potentially quite important because they blow holes into the cloud, which ionized gas theoretically can leave, and so on. The recombination rate depends on the local density and the chemistry and so on. It's very, very complicated. So I think a full-scale hydrodynamical calculation, for which you also need magnetic fields with full radiation transfer, and that's what one would have to do, is computationally completely out of the question. It's not. They can't even do it for a single star. Yeah? And so what we do is we take a shortcut. We just say there's a potential which changes with time. Yeah, and that stars move in this potential, but so it's an accurate n-body calculation, but the gas is just an additive potential. And that way we have three parameters, well, number of parameters: the mass of the potential, the scale, the size of the potential, and then the time scale in which the gas is removed. Yeah, and it works incredibly well to reproduce what we observe. Yeah.
What is this supervirial? What is this?
Sorry for using that term. Supervirial just means that the cluster is, the stars are moving too quickly. So you have a potential, you have a star cluster, the stars are moving in the potential which they self-generate, and so they are moving with virial velocities. They're not moving too fast, otherwise they would leave, and not too slow, otherwise the thing would collapse. It's just the virial velocity means it's a virial equilibrium. And supervirial means that there's too much kinetic energy, the stars are leaving. Yes, basically just, yeah.
Any other questions? If not, I think Pavel will be here today afternoon, tomorrow.
Tomorrow,
okay, so we can ask him anytime at the Institute. So thank you again.